You have to ask him.
Okay. You should charge it like a lawyer, like
yeah, exactly.
5 minutes, $1,000.
But science takes overhead, so it's
Right. Good morning, everybody. Welcome to day 4. I'm really happy to welcome back to Berkeley Susmit Jha. Susmit is currently technical director at SRI International, which I think all of us know is one of the leading labs across not just computer science and engineering, but a lot of other areas in the world. And over there at SRI International, Susmit is really the person who started a whole group in neurosymbolic computing and neurosymbolic reasoning, and then he's grown that group into one of the research powerhouses in this area. So I've actually been participating in multiple DARPA programs where Susmit has been leading teams, and his team has always been like the performer to catch up to. He's done many impressive things, especially over the last recent years, but he's also been one of the first people to make connections between formal methods and machine learning going back 15 years, so in his PhD thesis. So welcome again, Susmit, and looking forward to hearing about your talk on robust learning.
Thank you, Sanchit, for a really generous introduction. So today I'm going to talk about robust learning and how do we enable it by having principled out-of-distribution detection via multiple hypothesis testing. If you think about robust learning, then there are 3 main challenges, or at least dimensions of this challenge that you can think about, across which we need to be able to solve the problem to achieve really robust machine learning models. The first dimension is obviously about generalization, that how do we create models that are capable of operating in completely novel environments and are robust to adversarial perturbations. The second dimension is that are these models capable of at least some level of reasoning? Whether it's symbolic or not is a question about how do you implement it, but they need to have the capability to be able to reason about the world out there. And third, most importantly, is that they have to be efficient in terms of how much data we require to be able to train them, because there are many domains where the amount of data available is always going to be sparse. Also, in terms of compute, how much compute we require to be able to actually build these models, and the size of these models. And if you look across all existing AI paradigms, symbolic, neurosymbolic, completely neural, or LLMs, you will find that these paradigms can address 2 of these 3, but there's nothing out there, at least in the AI world, which is good at all these 3 spectrums. But at least we have one proof of evidence of such a capability that exists, like human mind has all 3. We are plastic enough to be able to actually very quickly adapt to all the situations. We have the capability to do reasoning, as well as we are very energy efficient compared to what these models are. So what we have been trying to do at SRI is to look at this kind of inspiration from how human mind works and think about how do we come up with an architecture of AI which can possibly have all these 3 characteristics. There is a theory of mind. There are several of those which have tried to explain how human mind works. One that goes by the name of predictive processing posits that the way human mind works is not through bottom-up kind of cognition, where we look at what the senses are saying and then try and interpret them, but rather we build a narrative. We build a story about how the world is evolving, and then we try to confirm that using our senses. And every time our sensor mismatches with what our story is saying, that is a surprise that acts as a signal for us to be able to revise our own story or the interpretation of the senses. And there's a lot of plethora of evidence that comes even more physically to be able to say that, well, this is how human cognition works. I'm going to use an audio that is from Ali Said's talk. If you have heard it, then probably this will not have the same impact. But if you have never heard this audio, hopefully this will give you some reasons to believe that maybe predictive processing or something similar to that is how human mind works. I will play an audio here and then ask you guys to guess. Could you guess what is being told here? Let me repeat that a few times. If you can have the audio be slightly raised. If you can guess it, just raise your hand. Awesome. Don't say that because it will bias everybody else. Sure. Okay, if you have been, you were the end too. I think you have been in meetings where I have played it once. So one thing here is going to be that I will play a second audio, which will be much more clearer. And we can reduce the volume if possible. And let me play the audio now, which is the non-noisy version of it.
I think Brexit is a really terrible idea.
Now, if I play back the noise, is there anybody in the room who can't really interpret it now? You all can, right? Because you got biased. And the really, really surprising thing here is that every time you will hear this now, you will be able to interpret it correctly. 5 years down the line, 7 years down the line, it will not change. I've done this multiple times over the last 10 years. I think Anil's talk is from like a decade back. And there are many such examples that you can find, because we are very good at being able to find these biases recorded and then be able to like interpret the sensors using that. We do that all the time with vision as well. We do that all the time with vision as well, but we do it so often that it's less surprising if you don't use the audio modality to illustrate this to folks. So if I show you this particular image and say, well, what is it? Most likely you won't be able to guess it. But if I give you the whole context now, then given the fact that you're looking at roads and cars, you will say, oh, most likely this is a car because I see some white pattern in a dark background, which probably is a car on the road. So we do build models, and models are how we are able to interpret what is happening in the world. And we took this idea and we thought of how to implement this. And obviously, everybody here who works in AI knows that this area rapidly gets disrupted it used to be every year, now it's almost every month. So the architecture that I'm going to show you is what is currently true. The architecture that existed 2 years back was very different, and most likely what will exist in a year will be slightly different again. But we are mainly changing the components about how we implement it, but the main paradigm remains the same. What we have is essentially a 3-layered system, which you are looking at the left. The first bottommost layer is completely neural, and it's responsible for essentially being able to make atomic decisions about let's say, what objects exist out there. So think of segmentation model, think of object detection model, ground in dino, these kind of models, which are going out, looking at the world, and then coming up with these atomic concepts. The second layer is a sub-symbolic layer, mainly because the model itself is not symbolic, but it is actually taking input and output, which happen to be symbolic. And that's currently implemented using these foundation models. And then finally, we have the logic programming layer, which is implemented using answer set programming right now, which is purely symbolic. And then you will see that you have top-down and bottom-up connections going up and down between them. Because what we do is that the bottom layer is going to find atomic concepts, feed it to the foundation model, and the foundation model is built in a larger narrative of a longer, wider context. And then based on its own prediction, it's going to re-predict what the bottom layer should have seen. And the mismatch between these that you see here, the predictions that the bottom layer made and the top layer made, that difference is the surprise. Because these two abstraction layers, which are working at completely different spatial temporal levels, they are disagreeing. If they're disagreeing, then we are surprised because our narrative about the world has actually no longer consistent. Similarly, between second and third, we have the same structure. The foundation model is coming up with some predictions, and then we have an answer set programming layer trying to reason with it. And if they both disagree, we again raised a surprise. These two act as a runtime assurance method now, because we are able to quantify how uncertain we are. If we ever take the system into a novel scenario, and that novel scenario is something that we don't generalize to, what would happen is that these different abstraction layers will start disagreeing with each other, and we can go back and say, well, our runtime assurance is low, we are really surprised. Apart from being able to provide runtime assurance, what we have found is that this architecture is much better at being able to learn from small amount of data. So New Scene is a data set that has been around for a while. It has scenes from Boston and from Singapore. And it has some classes which are minority classes with less fraction of data, motorcycles and bicycles. And you will see there that the typical state-of-the-art methods perform much poorly compared to what we can do. So we can learn with less amount of data. We can also handle perturbations like occlusion very well, which is not very surprising because we are able to exploit the context similar to the examples that I showed you. This architecture is also exploiting the larger context to be able to make predictions. So obviously things like occlusion, adversarial perturbations, this kind of architecture is going to be much more robust to it. And there's a plethora of different neurosymbolic architectures. A lot of them have several different advantages. one key distinction I will point out between what we have and what exists out there is that usually what you see is a very layered architecture. You have neural model feeding into a symbolic layer, and then the symbolic layer will make decisions. Or you have a symbolic model feeding input into a neural layer, and that's going to make decisions. What we have here is, as I mentioned earlier, there is a cyclic sort of like loop between these models. And we believe that this self-stabilizing loop is the key reason why this becomes much more robust. Because to be able to now fool the system, you have to fool the system at multiple levels of abstraction and have them be consistent with each other, which is really challenging. Yeah.
This symbolic layer, the logic program, is it manually constructed?
Good question. Coming up.
Okay.
Lots of slides to go. So, so far, everything I described was to make things a little simpler by saying that, well, each layer is making decisions, but we are in the AI machine learning world. Decisions are not going to be very qualitative, binary, right, discrete. Rather, what we do is that each of these layers are going to make probabilistic decisions. They're going to tell you like the distribution over which they are confident about. So if you have object detection, you're not going to come back and say, I've detected object X. Rather, you will have a distribution over the classes. So Surprise is going to then look at the disagreement between these distributions. There are a plethora of methods to be able to compute that, scale divergence, Weierstrass distance. They all have their advantages. I'm sure somebody here in the room can give a 6-hour lecture on that. We have tried many of these, and depending upon which circumstances, what kind of modality you are in, one of these will work better. But the key thing now is that for us to be able to implement what I described, it's very important that each of these layers has a good way to be able to quantify uncertainty. It's able to tell you that how confident it is about each of these decisions that the model is making. And one area that has rapidly grown over the last, I think, 6-7 years, which relates to this, is out-of-distribution detection. That if you can't quantify uncertainty all the time, at least you want to be able to say that, well, this is the input on which I cannot trust this particular model. Now, going back all the way to 2017, there was a paper, Guo et al., which looked at the improved performance of the deep learning models. I think at that point, this ResNet in 2016 was the state of the art. They compared with LeNet from 1998. And what they showed is that despite the fact that the accuracy had significantly improved, the average accuracy, the model had become really miscalibrated. So what you're looking at here is a plot where at the x-axis, you have the confidence of the model on different buckets, and y-axis is the accuracy. If your model is well calibrated and is able to quantify its uncertainty correctly, what you should see is that this should track the x equal to y line. Because if you're very confident, you have to be more accurate. If you're less confident, you have to be less accurate. And what happened is that between LeNet and ResNet, the accuracy improved, but the calibration really became much worse. We also looked at this problem way back in 2019, and we looked at how to combine things with explainable AI. And we had a newspaper where we showed that, well, you can actually use explainable AI methods to be able to improve the calibration of these models. And then more recently in ICSI this year, we looked at these really large models. So with large models, at least you see a much higher generalization. I'm sure everybody has played around with ChatGPT or Claude or some of these models, and they are pretty good at being able to generalize to novel scenarios. And what we found is that for code models, the same story repeats. The larger the model, the worse the calibration is. So uncertainty quantification of these models is not really yet a solved problem.
Question?
Yeah.
Well, two related things. One is for the ICSI 2025 result. What do you mean by calibration?
Good question. So there are many ways to be able to measure it. I will describe one. So one way to measure it would be that you take inputs and you split them into, let's say, a random set of 10 buckets. For each of these buckets, you compute the average confidence of the model and the average accuracy of the model. If the model is well calibrated, your average accuracy and average confidence should align with each other. So on x-axis, what you're looking at is a confidence. Y-axis, you are looking at the accuracy. If the model was well calibrated, you'd see that all these histogram bars would track the x equal to y line. That would mean that the model is well calibrated. If it shifts this side, that essentially means that, well, my confidence is really high, my accuracy is low. So the model is actually overconfident. It's making mistakes with a higher confidence. And that's what typically we have seen with smaller models and larger models. There are other metrics as well. You will see a bunch of these other metrics listed here. In the paper, we describe them. Like there's beer score, and there are lots of different ways to be able to like measure it. This is the simplest way to measure it.
And how do you make correctness numerical quantity? So is it that you have a set of test
Right now we
cases
are
and it's the fraction of tests that are passing?
Yes.
Or what's the thing?
Right now we are talking about discriminative models. So we have data on which we have supervision available. We know the labels. So we have some set which is a test set. On test set, we can evaluate the model and see whether its accuracy is correct.
But this is for code, meaning is it for code generation?
Oh yeah. So this code model, the DIPy bench, you can use it for like the code model can be used for multiple purposes. One of them is summarization, and for summarization, you could have things like what is the function that this corresponds to. So you turn this into a discriminative task, and then you're able to look at the accuracy. Right. And even for, I will talk about generative models as well. We have looked at calibration and uncertainty quantification for generative models. You do the same thing with semantic clustering. That will come up later as well. But I hope what calibration means is more or less clear. There are many metrics for that. And obviously in the paper, we describe some of those. Now, to be able to talk about out of distribution, one big challenge is that for any of these models, what is in distribution is becoming more and more difficult to define, right? So it's not really like, at least in my opinion, a very monolithic concept that what is out of distribution, despite a huge set of papers which talk about this, some of our own papers. What we looked into a while back was to try and understand that what are different sources of why something would become out of distribution. It could be because of epistemic uncertainty, aleatory uncertainty, it could be class conditional. So there are a variety of different reasons why input could become out of distribution. And that gets reflected into, if you look at like all these methods that have come up over the last 7-8 years to do out of distribution detection. There are a bunch of those. I think the famous ones are the Mahalanobis distance, Odin, Graham matrix. But there are many of those which are listed here. This is a really nice survey paper out there which talks about it. All of them do well on some classes out of distribution. And my conjecture is mainly because what kind of OD you're looking at determines which of these methods is going to work well. So we looked at these methods, and what we realized is that to be able to create an effective way to quantify uncertainty and be able to detect out of distribution, we need to be able to combine all of these measures in some way. So think of them each as a score. And for each score, I can now define some sort of hypothesis test where the null hypothesis will be that, well, this input is actually in distribution, and then see whether I have enough evidence to reject the hypothesis or accept it. But I want to do it with all these possible scores, right? Because there are all these different methods to be able to do detection, some that we came up with, and a lot of this which has been proposed in literature over the last 10 years. So how do we combine them is an interesting challenge. And imagine like, just for a moment here, to understand the challenge better, let's say that we have two different scores, T1 and T2. They happen to have the mean to be 1 and -1, and the standard deviation is unit. If you combine them together in an ad hoc manner by just combining these through simple addition, T1 plus T2, now you end up with a score which has the same distribution when the data is in distribution and when the data is out of distribution. So the power of the score to be able to distinguish between OD and in distribution is completely gone. So clearly, any sort of like ad hoc combination of these scores will likely not work. We need to be able to figure out how to combine them in a much more systematic manner. This is where we looked at the literature on multiple hypothesis testing. And we said, what if we actually treat each of these scores and the test corresponding to them as a separate hypothesis test, and then we want to combine them all together. So imagine now for each of these core functions, we have a separate hypothesis test, and coming from a formal background, we are going to take a worst case kind of like a view here and say that if even one of these tests is going to say that, well, this is out of distribution, that's what I will declare it to be. So all these hypothesis tests have to all agree and say it's in distribution for me to accept this data is something on which the model can actually make predictions correctly. So, and one other thing I will quickly mention is because we don't have often access to intrain distribution, which is where I think probably Sanjay's question was going to as well. What we do is we use conformal p-values and not real p-values because we don't have access to the trained data. And we instead keep a very small calibration set. And how do you construct the calibration set is obviously challenging in itself and a whole together talk. But once you have the calibration set, what we can do now is that we can compute the score for each of those different methods for OD detection. And then we can compute the p-value, which will take the calibration set and compute the corresponding score there, and essentially look at the fraction of those, the fraction of number of points in the calibration set which have a higher score, and use that as essentially the p-value for that particular score. And then the way we combine them is by actually ranking all these p-values in the ascending order. So all these QIs are the p-values. They have been ranked in the ascending order. And then for a moment here, ignore the CK value that you're looking at. What is happening is that alpha is a total mass of like how much false alarm guarantee you want to give. So maybe you can tolerate 5%, 2.5%, some level of like false alarm guarantee. You take that alpha, and then you can split it across all these k different tests that you have, and then assign each of these p-values that much of leeway. And if any of those violate that, you will say, well, I will reject the combination of these hypothesis tests and say that this is out of distribution. The CK is an interesting correction. It's a bit technical for me to go here, but in the paper you can look at that. That allows us to be able to essentially prove some guarantees about this. And we can compute the size of the calibration set based on this to say that, well, if you have this right size, which obviously will grow with as the alpha becomes smaller because we want smaller and smaller sort of false alarm guarantee, it will also become smaller when k becomes larger. That is, you have more number of hypothesis tests available. And ultimately, what we are able to give would be a pack kind of a guarantee where we'll say that, well, if something is out of distribution, given my calibration set, then I can bound it with my this alpha, which is my overall false alarm guarantee, with a confidence 1 minus delta. What was really interesting is that when we ran our experiments, then for low alpha, which is where you would typically operate, because you'd want your false alarm guarantee to be low, the actual values and the bound was close to each other. All of us who have tried to do theoretical work realize that bounds often are orders of magnitude far from where the reality is. So at least to me, what was really fun here was that not only we have a bound, it's a tight enough bound experimentally as well. And then, as it has to be the case for MLAI papers, we did a lot of experiments with different architectures, with different in-distribution, out-of-distribution data. And what we found is that if you look at Mahalanobis, Graham, Energy, a bunch of these different methods, the way to combine them with our method seems to be able to do better compared to any of them in isolation, and many other ad hoc ways to combine it. JD.
All right, so a quick question on how this is done. Like, it seems like what you're doing as building blocks is individual tests over the statistics.
Yeah.
And then they are combined.
Yes.
Right. So I was wondering if you guys considered the kind of a joint test, in the sense that this, I feel like somehow it's not taking correlation among those statistics into consideration, because
Yes.
each one is done separately.
Absolutely, JD.
So
very good
you
question.
might be suffering power, right?
Yes, absolutely. Very good question. We are cognizant of that there is this limitation, that some of these methods actually are correlated, and we could exploit that. We currently don't do that. This actually influenced our choice of the scores that we took, because intuitively we know that Mahalanobis distance often captures epistemic acidity very well. Graham matrix is going to capture mostly style kind of features, not so much the actual semantic content. And the energy is more about the electrodic stuff, because you're looking at the softmax values. So we deliberately did pick score functions which are going to be somewhat uncorrelated so that we can combine them well. But that's an excellent question. That's something that we are looking into, and we would love to be able to like work on it if there's interest by you or others here. Okay, so we also did then extend this entire thing to be able to like work with video kind of data, time series data, because obviously not everything is static. And we also looked at like how do we take advantage of invariance and equivariance with respect to transformations, especially if you think about embodied AI, robotic kind of applications. It's not just that you're looking at the input, you can do experiments with the input and then look at the result of those experiments as some sort of like a conformal set, and then be able to run the same thing that I talked about. So apart from these extensions, what I will mention is that I focused a lot more on the entity recognition, how to do the uncertainty quantification here, but each of these layers have to deal with it. How much time do I have, Sanjit? Oh, okay. Yeah, plenty of time. Okay, so the second layer is the one which is responsible for some level of compositional reasoning, right? We have got all these entities and we need to put them all together, but you could have surprises there as well. And images are really good modality to be able to convey the idea, but the same idea transfers over to purely cyber setting to any other modality. So for image, if you, for example, look at this, you will see like there's a keyboard here where there should be a traffic sign. But individually, if you look at each of these components, right, nothing in the scene is new. This is something that the machine learning models are aware about. So the bottom layer will not be at all surprised with what it is looking at. But the middle layer is going to say, well, when I combine these things together, the keyboard should not be there. Or for the car should not be hanging up in the middle of the house, right, at some height. So we looked at ways to be able to go and essentially quantify uncertainty here. And earlier, what we tried was obviously to look at graphs, because graphs could capture these spatial reasons, spatial sort of like constraints, and then be able to do out of context, which would be the analog of out of distribution in a more compositional setting, and be able to detect that, well, these are out of context inputs. And then more recently, what we have done is a variant of it, which is what I'm going to focus on, and then compare with graph-based approaches and directly query in visual language models, because obviously one baseline that exists today is that have you called ChatGPT. So we have done that experiment as well to see how we perform. In terms of being able to look at more sort of like our these large models, we have two different approaches that we have tried. First approach is to do with semantic clustering. So here the idea is that you call the model either by rewriting your prompts in different ways, or you raise the temperature to be able to create diversity. And then you look at the output and you try to do some sort of clustering over what are semantically similar. So going back to Sanjay's question, like what is truth, right? Because once you're in the generative model space, how do you know that you're actually accurate? And you're no longer in the sort of discriminative model space, so you don't really have like n classes. But what this kind of approach allows you to do is to look at all possible outputs, cluster them, and then be able to look at heterogeneity within the clusters and the number of clusters. And there are many ways to be able to combine them together to come up with the uncertainty score. That's what we have been looking at. But again, that's an approach that I will not focus too much on. We have a new line of work which we looked at, which was about actually trying to fine-tune the model to make it well calibrated. So I'm sure you guys are familiar with LoRa, which is a really efficient way to be able to adapt the model, fine-tune it with less amount of data and make it be able to learn new skills. What we looked at is that can we actually have a Bayesian LoRa, where the LoRa itself will be a small Bayesian network, and it will learn to be able to assign uncertainty to the predictions that the large language model makes. And this is the rough architecture of how it looks. If you're familiar with LoRa, what happens there is that instead of training a N cross D, sort of like a large matrix layer, you decompose it into two smaller matrices using this reduced dimension of R. One simple approach here would have been that you just take this A matrix, which is R cross T, the reduced rank, and the D is the dimension of your internal representation, and then say that, well, we are going to split this into the mean and the sigma, and then use this as the Bayesian network. The problem here is that you will end up now magnifying the number of parameters by twice. You will have two R cross T parameters that are going to be learned as the Bayesian representation. What we realized is that we can actually capture the uncertainty in the reduced space itself. So in some sense, what we do is that we take A and we do the single value decomposition of that to be able to split that into two other matrices U and B, have a diagonal matrix, which is in the sort of like R dimension space, and then have the uncertainty be encoded there. This really reduces the number of parameters we have, and surprisingly does well in terms of how we are able to assign uncertainty. So what you're looking at here would be the number of parameters and then the accuracy. What you will see is that our approach is able to drastically reduce the number of parameters required and still have the same accuracy. And not only the accuracy remains the same, when we go back and look at our sort of like the calibration error and NLL negative log likelihood, which is another way to be able to look at how overconfident your model is, what we end up is that our method does better even in terms of calibration. So this would be an example of how you can take even large language models and use Bayesian LoRa kind of approaches to be able to make it more uncertainty aware. Yeah.
So this is, I think everything you've talked about so far is in the context of making the individual ML models more uncertainty aware and more trustworthy in that sense, right? But have you tried to then look at this, in fact, the predictive processing architecture you talked about at the beginning in the context of a larger system in which you're integrating these components, maybe in a in a closed loop
Yep.
CPS type
Great
setting?
question, Sanjit. So I will split it into two sub questions here. One would be that right now I've been talking about uncertainty here. I described uncertainty here, and then I will talk about there as well. The actual architecture that we have, we call it Trinity AI. It itself is a system now because it has multiple different machine learning models. And we need to be able to compose the uncertainty across all of them together. This is where we utilize the predictive processing kind of intuition to say that, well, we are going to look at the distance between these distributions that we compare and use that as the runtime assurance. But this is still the AI system. This is going to be part of a larger system. Let's say that this is deployed on top of a drone. And the drone is now going to operate, and there's a controller attached to it. It's going to decide what the right plan is, what the right waypoints are, and then move across that. We have not looked at uncertainty composition across that kind of a larger system. We are still focused on just this AI block. And we are saying that, oh, for this entire thing, now, can I make sure that whenever I make prediction, we can output some level of confidence, which is well calibrated. That is, whenever we are confident, we are also accurate.
I see. But also, is it true that these different levels, it almost seems like these are parallel systems, decision-making systems that you're comparing the decisions over, right? But really, my original view of this when you presented this was that it's a layered architecture where they're actually all working together to make the decision, as opposed to you're running them independently, then comparing the distributions. Did I misunderstand?
Yes.
Okay, so can you clarify that,
needs
please?
To be figured out.
Yeah.
But because running in parallel, running together, they both, at least to me, sound similar. But let me try to mention
No.
what is happening.
Is there a feedback loop, or is it that
okay,
you are just running the sub-symbolic and the symbolic and the neural layers?
I see where you're going with it. So 3 points here, which I think will help clear up that confusion. One is that, yes, all these three are running in parallel, right? There's a feedback loop happening. All three are always running in parallel when you at inference time. What is happening is that each of them are working at different levels of abstraction, right? Like as you go up, the context that you're capturing is much larger, both in terms of space and time. The bottom layer, like if you're, let's say, doing video processing, the bottom layer is going to focus mostly on each frame. The multimodal model is going to sort of look at maybe a few frames, a few seconds, right? The top guy, which is logic programming, that is trying to do situation understanding across the entire stream. Now, that's the inference time architecture, right? When you're learning it, are you learning it by combining all of them together? Or are you actually trying to learn them by having them be learned separately and then put them together? Currently, what we do is that we have these learned separately. The uncertainty quantification that I presented, that has to be jointly done. So you need to be able to now calibrate the whole system together. You do the calibration for each of them, and then you need to make sure that the combination that you produce, which is where the multiple hypothesis testing idea that I mentioned to you generalizes very well, because each of these UQ uncertainty quantification scores that I've talked about just becomes a separate metric. And then you have to combine them all together with some false alarm guarantee. Does that answer your question, Sanjit?
To some extent, but also I think what I didn't understand is how can you compare the distributions when the outputs of these different layers are different?
Yeah,
right?
because at this point, so if you look at this, again, I think there are two interpretations here, Sanjit. Like one would be that if you're looking at this particular block, they are predicting the same thing. The bottom layer is trying to predict what entities it is observing. And then this layer is saying, okay, I will try to reinterpret based on my larger context and say that what should you have observed? So let's say that for some reason, the bottom layer could not find a vehicle because maybe the vehicle had an adversarial patch or something. But this top layer had seen vehicles before. And because of persistence, it will say that, no, I have to expect a vehicle here. At that point, the distribution of what entities are being detected sent by the top layer and the bottom layer will not match. And that will mean essentially that we are surprised. Does it make sense?
It's still a bit abstract. It'll be great if maybe you can talk offline to see a more concrete example of this.
But again, the other part the other way to interpret your question here would be that all these are computing distributions. How do you combine it together? Because now the score that we are looking at is the overall confidence of the model. We're not assigning that to any part of the input and saying that, well, this decision is what we are telling you we are unsure about.
Okay.
We are saying that the overall stack, how sure I am.
Okay.
And
then
that has to be just
Sure.
well calibrated.
And then the other question I had is essentially about the architecture is the last line, right?
Yeah.
So what are the guarantees you have about self-stabilization?
Yeah.
And again, if this is a longer conversation, we can have it offline.
Yes, this architecture has been developed over 8 years, so I'm focusing on some aspects of it. But that's also a very good question. That how do you make sure that when the uncertainty actually rises in any of these layers, how do you go and revise that particular model, which is what makes this entire thing stable? That is something that definitely we can talk about offline. Jedi?
Right, I want to build on that
Yeah.
question,
Right.
right? So maybe you already answered it, but basically, if the middle layer says here has to be some object.
Yeah.
Bottom layer says I don't see it. Maybe
Yeah.
it's fooled by adversarial patches, whatever. Ideally, you want to take that and say, hey, retrain the bottom layer because
Yes.
we really should have that.
Yeah.
But is it true
We
that
don't do
at
that.
least for now you're not doing
We
it?
don't do that. We rather just record it as a score, a runtime assurance score, and we produce that saying that we are not confident for this particular prediction. Using surprise to learn, that becomes tricky because you can have feedback loops. We can end up just completely destroying your model based on local surprises that you have, because which part of the model to revise? Are you going to change the lower one or the upper one? That's a very tricky decision to make. So we don't do any kind of like runtime retraining. And human mind seems to do that. So we haven't figured out yet how to do it.
Okay, thanks.
Okay, so we've had quite a few questions. So what I will do is that we were here. So just quickly showing you that if you are looking at all these data sets that exist for out of context, this method seems to do well without any fine tuning. And our own method, which is to use graph neural networks, required significant amount of training. It required a context to learn these sort of like what other valid compositions. That seems to underperform. And then if you just call a visual language model, which you're using here without all these like other layers, then they clearly do poorly. But there are limitations, obviously. Some of the failing cases that I would mention here is that we don't know how to do quantitative reasoning yet. So if you're looking at scenes like this, where there are lots of toilet papers, right? Or this particular one where we have a motorbike, which is really small. These are things which the visual language model will not capture. When we're doing logical reasoning, if we have not really programmed that in, saying that, oh, go and count the number of these toilet papers, or go and look at the size and try to characterize it, this doesn't get reflected anywhere in all three layers that we have. So these are the kind of surprises which will make this overall architecture go astray.
I didn't understand the comment you made just now, that the vision language model doesn't capture it. I mean,
yes, so this is
the caption does capture it in some way, right?
Lot of rolls of toilet paper. What is a lot? A lot could be perfectly in distribution if there are 3, 4 of them. But any human will look at it and say, well, this is not in distribution. This is out of distribution. So if you're trying to
But what's the question you're asking the vision language model?
One of the applications here is to do situation understanding, where the question is not something that you know. You expect AI to be able to tell you that, oh, this is the situation and this is what I'm observing. So imagine like a setting like ISR, like you're doing surveillance and reconnaissance, and you deploy this system and you want it to be able to tell you what is interesting that is happening out in the world. And any of these scenes will not look interesting to the architecture that I presented because it's not capable of doing quantitative reasoning. It will look at all this and say, perfectly fine, there are lots of toilet papers. There's a man riding on a small motorbike, nothing surprising about this. But any human will look at it and say, well, this is surprising. This is something we have never seen before. It's something interesting that we should report. You seem unconvinced. What part is...
No, I didn't understand the point the slide is making, actually.
So what is the limitation of our current architecture, Sanjit? That is the point. So we can do reason over the compositions, but what is the aspect of the input that we will be unable to actually reason about? The quantitative reason is not captured anywhere.
But I mean,
it's not captured by the logic program.
What was the task that the VLM was doing here? Was it just coming up with a caption?
So that's a good point.
Was it? Did you ask the VLM specifically, like, is this a image that I should be surprised about?
Right. We don't try to formulate that particular prompt because that would make it very ad hoc. It's the logic program which will decide what query has to be made to the multi-model model. So the logic program will execute its inferences.
And so in those cases, the logic program, what did it do?
The logic program will go in and say that, well, I'm looking out in the world and I expect, let's say, toilet and these, because these are entities that I've seen. And I, as part of the background knowledge, I would want to be able to know that which thing is to the left of what's the spatial directions, what are the quantities. So you have pre-programmed sort of like aspects of the inputs that you're going to query the large language model about, but you have not programmed it to be able to do quantitative queries. So it will fail on that. Now I could go and add quantitative queries for some of these entities, but for most of them, it's not going to be interesting. So what would be really good is a way to be able to sort of like either within the logic program, realize that when quantitative becomes interesting, or for the middle layer to natively learn to start reporting quantities when they are interested. Which of these layers will deal with the quantitative reasoning? That's unclear, but somebody has to. Currently, our system does not do that.
I see. Well, I mean, speaking of failure cases, I think the gravel road, that caption seems to have missed the point in some sense, right? Of what makes this image.
Yes, all of these are the same.
No, but I think I would argue that 189 is reasonable. It's saying it's a man riding a small motorcycle. It may look.
Yeah,
it's not implausible.
I think your comments are making a very good point here, that gradually as we are making this architecture and in general AI more and more smarter, we are walking into a subjective territory where what is correct from one human to another would also differ. Now, how do I define correctness becomes questionable. I think for many people, if you look at this particular bike, they will say that, well, this is an unusually small bike. Right?
Sure.
It's not just a small bike, which is acceptably small, but not arguing too much about the smallness and the quantity here. The key thing here is that all of these, if you look at the failing cases, the common characteristic is that the quantitative part is what is not being captured, because none of these layers currently know how to capture that. And I think the key thing, again, that will emphasize is that which of these layers should do that is also not quite obvious to us. We don't handle that. I think going at the last layer here, I hope 5 minutes at least. Okay. So for us to be able to now take the sort of like output of these visual language models, let's say, and be able to push it up to the logic program, we need to solve one problem, which is auto-formalization, because we need to compile whatever been obtained in these captions and then push it back to the logic program as like what statements we are aware about. Over last 2-3 years, we have found that these large language models have become really, really good at auto-formalization, especially when you look at syntactic accuracy. And if you guys are familiar with Wolfram, you can go to their website. They maintain a whole list of language models and how accurate those models are in taking word problems and summarizing them into the Wolfram language. And it's alarmingly high accuracies across different families of large language models. And we have observed the same thing here. But semantic accuracy, which is, are they actually capturing what you wanted it to capture? Because it could be syntactically correct, but then miss a lot of key details. That still remains very challenging. We have a whole loop of using counterexamples to guide and be able to create those formalizations correctly. But once we have that, then I will go a little faster here because
Excuse me,
we are running out of time. But
just previously a folio. What do you mean that the accuracy 61%? That did you detect the errors in the folio data sets or
no, in the formalization that the language model did? So it missed predicates, or I think you had a very good example yesterday, right? Like of what is the predicate before tenure,
yeah, like
right?
Yeah,
so it ends up doing something funny. So that's what the semantic accuracy is, because syntactically, right, something that will just pass the check for ASP silo system, that is actually pretty high.
Thank you.
Then the other part is that, okay, we have these uncertainties coming from these sort of like intermediate like ground observations that we are doing. We can be able to like quantify uncertainty on nearness because the middle layer is going to compute all that. Now we need to put all of this together to be able to do the inference on logic programming. I will skip the details here. We have tried to implement it numerically because often these systems work on GPU. So if you can convert all of this to a tensor programming problem, the entire thing becomes much more homogeneous and faster. The details of this are obviously in the papers that you can look at. It ends up becoming a large tensor computation, which is iterative. And one thing I will emphasize here is that we use an anytime solving kind of a method so that we can terminate in the middle and discover all facts that we know to be true till that point, and then be able to push it back to the middle layer. So this is not goal-directed kind of reasoning. Rather, what we do is that we try to take all the facts that we know and infer as much as we can, and then try and confirm it from the layer that is below us. So And then we have also looked at like verifying these systems against semantic properties. In interest of time, I will not go there because then we will have time to be able to have more questions. So let me stop here. What I presented to you was how do we actually take the overall cognition problem, be able to break it into something which is inspired by predictive processing, have these kind of different layers, the 3 layers, which try to capture the problem at different abstraction layers. And then what we realized is that for each of these layers to be effective, quantifying uncertainty of their prediction is very important. And then being able to look at the mismatch between their confidence across these layers gives us a single confidence score for the overall this cognition architecture. And this makes it much more robust when we deploy it in novel environments. As I think questions from JD emphasized, this is a more sort of a runtime composition. We don't currently utilize surprise to be able to train these different layers. That's the next step that we want to work on, that how do we do it in a way that is well principled so that we know if there's a mismatch, should we be actually revising the upper abstraction layer or should we be doing it for the bottom one? That does seem to be challenging because we as humans have a very good intuitive feel of when we change the story, the narrative of the world, and when we actually try and reinterpret our senses. That seems to be difficult, at least for us, to do that in most of our AI setting. Thank you.
So I have a question on like why 3 layers?
Yeah.
Is it more a, I would say, implementation consideration, like just because currently as things stand, you have systems that's already built for 1 layer and so on? Or is it something fundamental about it? Like a counterpoint is like, why not just like bottom layer neural, top layer symbolic?
Yes, it started with 2 layers, right? Kahneman's system 1, system 2. That's what we were going after. We said predictive processing via Kahneman's architecture. That's what we want to implement. And earlier we used to have the bottom layers to be all these sort of like smaller models. And then on top of this would sit a graph neural network. What we gradually realized is that graph neural networks are not really very good at reasoning. You need a pure symbolic layer on top of it. We tried using first order logic, but then first order logic has a problem that if you have an exception, if you have a contradiction, your entire knowledge base gets corrupted. So we required logic which would actually deal with exceptions. That's what pushed us to go to inductive logic programming, as I said, programming. Now, the middle layer that used to be graph neural network, as I tried to show quickly with some of our experiments, we realized that these visual language models are much better. Without much fine tuning, we can get better performance. So to answer more crisply, Jerry, this is a choice which is based on the current components that exist out there. Most of the cognitive literature out there, which has looked at human mind, argues that there are only 2 systems. But it is possible that that itself is an abstraction of how we are trying to define human cognition. There may be multiple layers. Why are there not 4 layers is another question to ask, which is driven by like how much implementation constraints we have. I think despite the fact that each of these layers are clearly capturing something different, right? They are looking at very different abstraction layers. It's hard to make a mathematical argument that this is the most optimal one. And we wouldn't be able to discover a 2-layered architecture or 4-layered architecture, which would be better. But right now we require all 3 for this to work.
So I wanted to point out again that if we don't look at the particular, a single decision, right? If we look at a collection of decisions by the different things, then you could get away with actually not using any distribution whatsoever, right? Because you're just looking at the number of times that the different things agree and disagree.
Yeah.
And then that would be an empirical, right, way of, but then it would have to be a system where you can allow, right, that collection of multiple decisions to then be able to do this empirical
Absolutely.
approach.
And now it depends on what kind of assurance feedback do you require. Is it the case that you deploy this architecture, you send it out on a mission, it comes back, and then you provide a single score and say, well, today I was 80% confident and I did 80% well? Or is it that every single frame, you want a score coming out and saying that, oh, now I am in a novel environment? So depending upon what is your sort of like rate at which you require the assurance metric, you can do it either at each decision level, which is what we are currently doing, or you can accumulate that and think of that as a distribution where the decisions themselves are not probabilistic, they're all discrete, and then create distributions over those. In many applications, actually, we want it to be at the level of decisions and be able to account for that. But I can see situations where you would rather aggregate it across the whole mission. Maybe like at the end of the day, the robot comes back and you want to look at like how confident and correct it was.
Let's say 10 seconds, right?
Yeah, yeah, yeah. You could do that too.
Any further questions? All right,
Cool.
let's thank
Thank you.
Susmit again.